All right, so let's do this integral. I'm going to think about it being separated around the addition. So you could make two separate integrals. You could do 0 to 4 e to the x dx plus root 3x dx 0 to 4. You could do that and make it two separate integrals, or you could do it all together. Since it's already separated, I'll just do it this way. So the antiderivative of e to the x is e to the x, and then I put this bar here to say I'm going to evaluate it between 0 and 4. And so then I'm just going to continue on continuing my work on this line. Before I take the antiderivative here, I know I need to separate the radical around the 3 and the root x, and the x, because the root is over the number and the x. And you need to have x to a power in order to find the antiderivative. So I'll just continue on this side. So doing this, I'd get e to the 4, subtract e to the 0, which is 1. And then I'm adding on. So this root 3 just carries along, and I take the antiderivative of x to the 1/2. I get x to the 3/2 over 3/2. So this is going to get evaluated between 0 and 4. So carrying along this first part, and then plus, I'm going to say this is 2/3 times root 3. Now I'm going to plug in 4 and subtract off 0. So I have 4 to the 3/2, subtract off 0 to the 3/2, which I know is just 0. So this gives me e to the 4 minus 1 plus 2/3 root 3. Let me make that bigger. And then 4 to the 3/2, you know that square root of 4 is 2, cubed, that's 8. All right. So now I'm going to take the integral, the definite integral, of this, which is going to give me tangent, because the antiderivative of secant squared is tangent of t. You know, these letters have to match to take the antiderivative, and evaluate it between 0 and pi over 4. So I have tangent of pi over 4 subtract tangent of 0. I know tangent of pi over 4 is 1, and I know tangent of 0 is 0. So there's my answer. This one here I want you to be careful with. I want you to make sure you see that this is 1/2 times 1 over u du. So notice I'm changing letters on you, right? As long as this letter x dx has x's inside, it's consistent, right? This dt has t's inside, it's consistent. Du, u's inside, so just changing the letters and keeping consistent. All right, so, oops, I forgot my limits of integration. From 1 to 5 is how you say that. So I'm just going to write it one more time. So integral of 1 over u du. So this is really important. I've been noticing it on homeworks. I haven't been taking points off it, but I want to make sure that when you take the antiderivative, you get ln of the absolute value of u. Then I can say plug in the numbers. So I get ln of absolute value of 5 is 5, minus 1/2 absolute, and ln of 1, absolute value of 1 is 1. I know ln of 1 is 0, so this is the same thing as saying this. And then I want you to know this is the same thing as saying this. Not that I care which way you write the answer, but this 1/2 in front of the ln can be put up in the exponent. This is a fine answer, and so is this. All right, so we need to know our antiderivative rules for 4 to the x. So the antiderivative of 4 to the x is 4 to the x over ln of 4. And here I'm going to evaluate between 0 and 2. So I'm going to substitute 2, so I get 4 squared over the number ln of 4, subtract 4 to the 0. Just going slow, so you see 16 over ln of 4 minus 1 ln of 4, so that gives me 15 ln of 4. Okay, now I want to make sure that you're very clear on the difference between the derivative of 4 to the x. So derivative of 4 to the x is 4 to the x times ln of 4. The antiderivative of 4 to the x is divide by ln of 4. So make sure that you've got the difference down. All right, this one here, it's this plus 2 up here is a problem. So I need to invest time fixing it. So this can be written, remember, if it's addition in the exponent, it's multiplication downstairs. So this is really what e to the t plus 2 looks like. And you know that e squared is just a number, so I'm even going to pull it outside. So now I'm just taking the antiderivative of e to the t, which I know is e to the t. And I'm going to evaluate it between -1 and 1. So I'm carrying along the e squared. I'm going to plug in the 1, so I get e to the 1, subtract e to the -1. And I'm just going to fix this a little bit. This is the same thing as saying this, right? E to the -1 is the same as 1 over e. So this could be written as e cubed minus e. All right. Oh, there it is. Okay. So this one here, I need to invest time in splitting it up around that addition. Remember all the antiderivative work we did. So this is the same thing as saying 1 to 9, 1 over x squared plus root x over x squared. All right, so I'm going to fix this. 1 to 9, I'm going to rewrite this as x to the -2, and I want to write this as an exponent, right? So this can be written as x to the -3/2. Now I'm ready to take the antiderivative, right? So add 1 to the exponent, x to the -1 over -1, plus x to the -1/2 over -1/2. And I'm going to take a step to fix this. Anytime I see negative exponents, I like to write them in the denominator so that when I'm plugging numbers in, I can see what it is more clearly. So this -1/2 in the denominator turns into a -2. And then this, well, -1/2 up here is the same thing as saying 1 over root x. Right, that is a -1/2. Okay, now I'm going to do evaluate between 1 and 9. So I'm going to plug in the 9. So I get -1/9 minus 2 over root 9. Subtract, so be careful with the subtraction sign for the second two terms. I want to make sure you're always using parentheses. So now I'm plugging in 1, so I get -1 minus 2 because the root 1 is 1. Okay, so what do I get from here? I get -1/9 minus 2/3, and then here I get a -3 subtracted, so that turns into a +3. And I'm just going to leave it like that. All right, so here I recognize my inverse trig functions. They're going to come up a lot, so make sure you're really comfortable with them. This one here is arctangent of x. And then this one here is arcsine of x, and it's between -1 and 1. So I'm going to plug in 1. Oops, I meant to plug in 1. 1, and then I'm going to subtract off plugging in -1. Okay, lots of computation to do here. So arctan of 1. So arctan of 1 is asking what is the angle that I can take the tangent of to get 1. And remember, arctangent has that restricted domain between -π/2 and π/2. So this will be the angle of π/4. This has the same thing. So inverse sine of 1 is like saying what is the angle so that the sine of theta is equal to 1. And sine has the same restricted domain, so this would be the angle of π/2. Okay, so that's the first. Minus. Okay, so now we're moving on to the arctan of -1. So that's like saying what is the angle that if I take the inverse, what is the angle that if I take the tangent of it, I get -1? Well, that's down here, so that's -π/4. And then plus, now same thing here, so this is asking what's the angle that if I take the sine of it, I get -1, and that's all the way down here, so that's -π/2. So what do I get? π/4 plus π/2 plus another π/4 plus another π/2, so I get pi plus, so 3π/2 finally. Okay, so this is a good time for me to make a comment about this. Okay, so this fundamental theorem of calculus, part 1, does not get used very often, right? This part 2 gets used all the time. So finding the exact area under the curve using this. So I'm in the process of grading your take-home quizzes, so you will never be tested or quizzed again on the take-home quiz material. You did it once. You did the long way of finding the integral, adding up infinite number of rectangles, right? Finding the limit. You did it the long way once, and it's done. You're never going to do it again. So this integral, evaluating between a and b, that's the antiderivative. This is how you're going to find the area under the curve, and that's what it's going to be.